Today, we are diving deep into a really novel framework for speech emotion recognition. It's called DDE-SER, and what makes it so interesting is how it tackles a core challenge in the field by mathematically taking apart the very components of speech itself. All right, so here's our game plan. First, we're going to unpack the big problem that has really stumped emotion recognition models for years. Then we'll get into the weeds of the clever two-part solution this framework proposes. We'll see how each part works, how it intelligently puts the pieces back together, and then, of course, we'll look at the results to see if it all pays off. So at the very heart of this research is this persistent, really frustrating issue in speech emotion recognition, something the authors refer to as the high arousal bottleneck. Okay, so what does this bottleneck actually sound like? I want you to think about someone shouting in anger and then contrast that with someone laughing with pure joy, you know? Both are loud, they're high-pitched, and they're just packed with energy. Well, to a machine learning model that's just looking at the raw audio signal, those two events can look remarkably, almost spookily similar, and that leads to a lot of confusion. Now, the technical reason for this mix-up boils down to the non-stationary nature of speech. So think of it this way. A single, steady musical note is stationary. It doesn't change much. But speech is the exact opposite. It's a constantly shifting landscape of frequencies, volumes, and textures. This rapid change makes it incredibly tough for a model to lock onto a stable, reliable emotional pattern. And here's where the problem really manifests. Imagine a spectrogram as a single snapshot of sound. In that one picture, you have everything tangled together. The long, smooth tonal energy from vowels is literally overlaid with the short, sharp bursts from consonants. It creates this messy, conflicted signal. And trying to feed that whole jumbled mess into a single neural network, well, it's a bit like asking it to unscramble an egg. It's just not set up for success. To get around this, the DDE-SER framework takes a completely different route. Instead of analyzing that messy, mixed-up signal all at once, it first decomposes it. It breaks it down into its fundamental and mathematically orthogonal parts. And when we say orthogonal, just think of it as completely independent. It's like separating the sound into two clean streams that have zero overlap. And this visual really drives the point home. On the one hand, you have the old monolithic approach, a single pipeline desperately trying to make sense of a jumbled input. On the other hand, you have this new idea, a dual-branch system, where each branch is a specialist, trained to analyze a pure, distinct component of that original sound. All right, let's dive into the first of these specialized branches. Branch A works directly on the raw 1D audio waveform, and its entire job is to isolate the underlying frequencies that make up the sound. So how does Branch A actually do this? It uses a powerful signal processing technique called variational mode decomposition, or VMD. You can think of it as an incredibly intelligent filter bank. It takes that complex, messy input signal and decomposes it into several simpler, cleaner modes or subsignals. But what's truly brilliant here is the feedback loop. The deep learning model itself actually tells the VMD algorithm how to best decompose the signal to get the most accurate emotion classification. It's this adaptive, self-optimizing system. Now, I know this equation looks intense, but you don't have to be a mathematician to appreciate what it's doing. The real challenge is that separating these signals is an incredibly complex, constrained problem. This equation, the augmented Lagrangian, is essentially a very clever mathematical maneuver. It transforms that impossibly difficult problem into a much simpler, unconstrained one that a computer can actually solve efficiently. This is the engine that makes the whole decomposition possible. Okay, so while branch A is busy handling the frequencies in the 1D signal, the second branch is looking at structure. It operates on the 2D spectrogram, and its goal is to separate the sound based on its texture and shape over time. And the goal here is to distinguish between two very different kinds of sound structures. First, you have harmonics. Think of the sustained tone in a vowel. On a spectrogram, these look like horizontal lines. Then you have percussives, like the sharp burst of a T or a K sound. These show up as vertical lines. By pulling these two apart, we get another incredibly clean, independent perspective on the emotional content of the speech. Here's how Branch B pulls it off. First, it computes a standard spectrogram. Then comes the really clever bit, orthogonal filtering. It applies a horizontal median filter to find all those continuous tonal sounds, the harmonics. At the same time, it applies a vertical median filter to find all the sharp, transient sounds, the percussives. The model then uses this information to create what are called soft masks that essentially lift the harmonics and percussives out into two separate clean spectrograms. This equation might look a bit complicated, but the idea behind it is actually pretty simple. This is the formula that creates those masks. For every single pixel in the spectrogram, it calculates a ratio. How much of the energy at this point is harmonic versus how much is percussive. Based on that ratio, it decides how to split the sound, resulting in two perfectly separated spectrograms, one containing just the tonal information and one with just the sharp percussive information. So at this point, we have two powerful, clean, and totally independent feature sets. The final piece of this puzzle is figuring out the smartest way to combine them to make a final prediction. And this leads us to a really critical question. I mean, we could just smash these features together, but would that really be the best approach? Does every single emotion rely on both harmonic and percussive information in the same way? The research suggests a pretty emphatic no. Right. Take sadness, for example. That emotion is often defined by its long, continuous tonal qualities, something branch A is perfectly designed to capture. But anger? Anger might be better defined by its sharp, aggressive, percussive sounds, which is the specialty of branch B. A simple, dumb fusion would completely miss that nuance. So the solution is this elegant technique called a gated attention mechanism. You can think of it like a smart audio mixer for the AI. As the sound comes in, the network learns to dynamically adjust the volume knob on each branch. If it detects a sad voice, it might turn up the volume on the tonal information from branch A. If it hears an angry voice, it might crank up the volume on the percussive info from branch B. It literally learns to pay attention to the most relevant features for each specific emotion, which leads to a much more nuanced and accurate final decision. Okay, a brilliant architecture is one thing, but the question is always, does it actually perform? So let's take a look at the validation protocol and the final numbers. You know, a model is only as good as the tests you put it through, and the methodology here is incredibly strict, for very good reason. They use leave one speaker out validation, which is crucial. It means the model is always being tested on a voice it has never heard before. This prevents it from just memorizing the speakers in the training set. And on top of that, they intentionally throw curveballs. They add noise, they shift the pitch, to make absolutely sure the model is learning the true underlying essence of an emotion, and not just getting fooled by some superficial artifact in the recordings. So on the benchmark German EMO-DB dataset, under these really tough conditions, the DDE-SER framework achieved a solid overall accuracy of 74.00%. Let's look a bit closer at this confusion matrix from the EMO-DB dataset. Now, notice that even with this advanced architecture, the model still mistakes happiness for anger about 28% of the time. Now, this doesn't mean the model failed. What it does is confirm just how difficult that high arousal bottleneck problem truly is from an acoustic standpoint. The key takeaway is that this architecture is starting to mathematically pull them apart, and that's a huge step forward. And here, this is where we see the payoff. This is where the model really shines. On a different dataset, RAVDES, look at its performance on the sadness class. It's fantastic, and this is a perfect demonstration of the dual decomposition working as intended. Sadness is an emotion characterized by those long, continuous tonal shifts, exactly what branch A's VMD is designed to isolate and analyze. This result is the proof in the pudding that separating the signals really works. So this brings us to a final, bigger thought. This model gives us a powerful, mathematically rigorous way to separate and understand complex, overlapping signals in human speech. And that just begs the question, where else could we apply this dual decomposition idea? You could be talking about anything from detecting subtle faults in a jet engine to identifying specific animal calls in a noisy rainforest. The potential for this kind of approach is absolutely vast.